Welcome to Lecture 7.6, Laplace's equation. Okay, so let's start with the main idea of the previous lecture, because that's extremely important for this lecture as well. So a function of n spatial variables, u of x1 to xn, is harmonic if any of the following three conditions hold. So the first one is typically taken as the definition. If the Laplacian of u, which is the sum of the second derivatives, is equal to 0. Equivalently, u is harmonic if it is a steady-state solution to the heat equation. So that's easy to see algebraically because this is the heat equation. And steady state just means that ut equals 0. So if we take a ut and we set it equal to 0, you see that the equation that we get is exactly this equation up here. So it's easy to see these things are equivalent. And finally, the third condition is the graph of u is as flat as possible. And so the way to think about that is if you have some sort of wire that's bent into some circular configuration and you dip it in a bucket of soap or you stretch plastic wrap over it, like if you're going to make it into a drum, then that surface you get is going to be as flat as possible. There's going to be no local minimums or local maximums. And that is the third characterization of what it means for u to be harmonic, as if the graph of u is this soap bubble-ish solution. So the PDE right here, Laplacian u equals 0, this is called Laplace's equation. And before we can solve the heat equation in two dimensions, or in any number of dimensions, we need to understand how to solve Laplace's equation first. And that's what we will do in the remainder of this lecture. Okay, so here's our first example. So this is Laplace's equation right here. So we can think of this as u being a function of two variables, which is the temperature, the steady state temperature at some position x and y. And we can see that let's see, how do we want to start? So this thing here is Laplace. This is the Laplacian of u. Or just uxx plus uyy is 0. And these are the boundary conditions. So notice that the boundary conditions happen when x and y are 0 and when x and y are pi. So we have a square region of length pi. And let me go over these boundary conditions one by one. Well, first of all, let me sketch this square region. So it looks like something like this. I'm not going to draw the back just for the moment, and you'll see why in a second. So let's suppose that x is going in this direction and y is going in this direction. So this point here is 0, 0. This point right here is pi 0. This point in the back is 0, pi. And then this other point is pi, pi. Okay. Okay, so this first boundary condition, u of 0, y equals 0, says that the temperature is 0 whenever x is 0. So x being 0 is this back boundary. So the temperature right here along this boundary is 0. Okay, so next, this second condition, let's do it. This condition says that the temperature is 0 whenever y is 0. So that's this boundary here. Okay. And then finally, the third condition, see if this color works. Yeah, this condition says that the temperature is 0 whenever x is pi. So that's this boundary here. So these three boundary conditions being 0 tell us that the temperature is fixed at 0 along here. And finally, this last condition, this says that the temperature is along the back boundary where y equals pi, that's this thing here, is given by this. And so that, remember, this is a parabola, and it looks like this. So what I want you to picture for this problem is the solution to this PDE is whatever surface you get. Let me draw this at the bottom of this just for reference. Is a function of two variables, and this is the surface of what you get if you take this thing, make it out of wire, and dunk it into a bucket of soap and pull it up. Or equivalently, if you make this out of wire and then you make a drum out of it, like you stretch plastic wrap or canvas over it. So what that's going to look like, let's see if I can sketch it. I'm not very good at this, but so it's going to look like this. And it's going to slightly get out. It's going to look like sort of like that. Okay, so now we understand what this PDE models, and you can see that, let me finish. Let's just say that this is a square region, and the temperature is fixed at the boundary for all time t, and let's suppose that the initial temperature is something else. So maybe it's really, really hot in the middle here. So if you were to graph it, it goes way up beyond the screen. Then, as time goes on, that temperature is going to dissipate, it's going to spread out, and this is going to be the steady state solution. Okay, so let's solve this now. So we solve these things always the same way. We're going to use separation of variables. So let's assume, oh, I forgot what color I had. Let me switch back to black. So we are going to assume that our solution separates. This is how we solve every PDE. So u of x and y. Now instead of f and g, I'm going to use capital, let's try that again. I'm going to use capital X and capital Y. So our function separates as a function of x and a function of y. So we are looking for a solution to this PDE that is a product of something of x and something in y, and we want to solve for capital X and capital Y. Okay, so let's take two derivatives, or let's take two partial derivatives. So because again, we're going to plug these things back into here. So notice that u xx equals x double prime y, and u y equals x y double prime. And lastly, we don't have to do this now, but remember, I always like to take my zero boundary conditions and plug those in and get a boundary condition for later. So let's do that. So these zero boundary conditions. Okay, so this is my own terminology. Recall, this is not something you're going to see in a book, but I like it. So this first one is this thing here. So u of 0, y equals 0. Let's write that down. So u of 0, y is, so that's capital X of 0 times capital Y of y, which is equal to 0. So look what we have here. So we have a number times a function is 0, so that number better be equal to 0. So let's write that down. So that means that x of 0 equals 0. Let's do the next condition, this one right here. So you see where we're going with this. U of x 0 is x of x times y of 0. So as before, we have a function times a number being 0, so that number better be equal to 0. Okay, so that means that y of 0 equals 0. And again, we know the function is not 0 because we were assuming that this solution is not 0. Well, we know it's not 0 because this graph is not 0. Okay, so finally, this last one. Let's see if this actually comes out in green. I haven't used green much in these lectures, but u of, that's not too bad, pi y equals x of pi y of y, and that's equal to 0. That tells us that x of pi equals 0. So these are our zero boundary conditions that we will use shortly. So all of this is pre-processing. Now we are ready to plug this thing back into our PDE. Okay, so let's do that. So let's plug back into the PDE. Okay, so u xx plus u yy, that equals this plus that. So that's equal to x double prime y plus x y double prime. And that's equal to 0, because our PDE is, remember, right here. Okay, so what we're going to do from here, let me actually box this. But let's divide both sides by x, y. So this thing holds. I'm going to divide by x, y. So if I divide by x, y, and I divide by x, y. Now the left-hand side, let's write what the left-hand side is going to be. So that's going to be x double prime over x, because in this first term the y's are going to cancel, on the second term the x's are going to cancel. So x double prime over x plus y double prime over y equals 0. I'm sorry. Oh no, that's absolutely right. Yeah. So this holds. We box this as well. So what can we say about this? So remember, we want to separate variables. That's what we've always done. So let's actually move the y over to the right-hand side. So if we do that, now we get, let's go back to black, I guess, x double prime over x equals negative y double prime over y. And now look what we have. We have this function which depends only on x. It does not depend on y, equaling this function which depends only on y, meaning it does not depend on x. So this quantity is independent of y, and it's independent of x, so it must be a constant. And so this thing is what we call the eigenvalue equation. Because there is some linear algebra behind the scenes here that we will not really see much of in this class, but take a PDE's course if you are interested. So what we now have is we have two ODEs. So we can write an ODE in x and an ODE in y, just like we did before. Okay, so we now have two ODEs. So the first one is x double prime equals lambda x. And we have two boundary conditions. We have this and this. So this is subject to x of 0 equals x of pi equals 0. And then our second ODE is in y. So that's this ODE. The same thing, just there's a negative sign, and we only have one boundary condition. So let's write that down. So this is y double prime equals negative lambda y, and we have one boundary condition, y of 0 equals 0. Okay, so this is what we have to solve. Once we solve this, we are done. Well, we are almost done. So once we solve this, then all we have to use is this boundary condition. And remember, we've solved this first ODE. This is a boundary value problem, and this is something that came up in all the other PDEs that we've seen. So we know the solution to this. We know that lambda, I'm just going to say, we know that lambda is negative n squared, and we know that x is sine of nx. So all we have to do now is solve this. So let's see. Let's clear this off, and then I'll solve these two things, and then we'll be done. Okay, so to summarize, we were trying to solve this boundary value problem, and let me sketch what that represents. It represents the steady state solution to the heat equation, where the boundary conditions are given as follows. And so you can think of this as this surface if we were to take this boundary and stick it in a bucket of soap. Okay, and again, x is in that direction and y is in that direction. Okay, so where we left off is we had two ODEs. So we had two ODEs that we had to solve. One of them is x double prime equals lambda x, subject to these boundary conditions that we've seen before. And then the second one was y double prime equals negative lambda y, and we only had one boundary condition here. So here are our two ODEs, and again, as we said, we know how to solve the first one. We've seen it before. So lambda can be any negative square number. So and then oops, I didn't mean to do that. And then x is just sine of nx. So x. So for each n we have a value of lambda, which is negative n squared, and for each n we have a solution, which is sine of nx. And I'm not going to put a constant in front of this because we can do that later. Okay, so let's solve this ODE right now. So now we can, so how do we solve the second one? Well, let's write it like this. So this is y double prime equals positive n squared, because we have a negative times negative n squared, positive n squared times y, subject to y of 0 equals 0. So this thing, you should look at this and you should think exponential functions, right? But remember what I said earlier. Anytime we have boundary value problems, it's typically easier to write your solutions using Sinches and Cauches instead of exponential functions. So we're going to write our solution here, as y of little y equals, I'll use A or B. I'm going to use capital A-N, cosh of ny plus capital B-N times sinh of ny. And again, we could use exponentials if we want to, but it's easier whenever we have a ODE like this and it's a boundary value problem to use Sinches and Cauches. Good rule of thumb. Okay, so now let's use our boundary condition. So y of 0 equals 0. Let's plug that in. So y of, actually I'm going to move that over to the right. So y of 0, remember plugging in 0 to sinh and cosh is the same as plugging in 0 to sine and cosine. So cosh of 0 is 1 and sinh of 0 is 0. So y of 0 equals a-n times 1 plus b-n times 0. So that's just a-n, and we know that's equal to 0. So that means that this term goes away because a-n is 0. So now we have our solution that y equals sinh, oops, I forgot my bn, bn sinh of ny. And if I wanted to, I could really drop this bn because I'm going to add the constants in later. So what we have is, I will drop that bn up here. I'm going to say yn of y equals sinh of ny. So this is our solution to this system. Well, it's not really a system, I guess. These two boundary value problems. Okay, now let's go back to the PDE. Remember where x and y came from. Remember we assumed that u of x and y, that we had a solution of the form x of x times y of y. And we found one. We said for every n, there is a solution this times this. So let me put a subscript of n in here. Yn, xn, and yn. So we have a solution of the form sine of nx times sinh of ny. So we have a solution, say that is a solution for all n equals 1, 2, 3. And notice I'm not going to use n equals 0 because if n equals 0 then we have the 0 solution, and that's, no, we don't need that. Okay, so let's use superposition now. So by superposition, we know that we can add up these as we wish. So let's say n equals 1 to infinity, and let's put a constant, let's call it bn times sine of nx sine of ny, or sinh of ny. So this is we say, let's call it the general solution. And let's talk about what this represents. So this represents all possible functions to Laplace's equation. So all possible soap bubbles where these three edges are 0. So what we've done so far, we haven't even touched this back edge yet. So all we've done so far is we've said let's suppose that we have these three edges. So we have a wire and these three edges are 0, and we don't know what this back edge is. Maybe it goes up like this, maybe down like that, maybe it's some wiggly thing. We don't know. But all we know is that we have these three boundary conditions, and this is the general solution. So it's gonna, so whatever happens, it's, let's just draw something. Let's suppose we did that. Then you can sort of picture what the soap bubble is going to be. It's going to be it's whatever that minimal surface. Maybe I shouldn't have drawn this surface is. Okay, so let's see how much of this I can. Oh, that's fine. So this is the general solution given these three boundary conditions. Let's use this last one now. So that's going to give us the particular solution to this full boundary value problem. Okay, so let's use the fourth boundary condition. And if we do that, so to do that, we have to plug in y equals pi. So u of x pi, so let's plug in pi, see what happens. So when we plug in pi, for y, we're going to get sinh of n pi. That's a number. Let's move that out in front. Okay, so this is going to be, keep forgetting that. So n equals 1 to infinity of bn sinh of n pi. This whole thing is a number times sine of nx. And we have to set that equal to this, x pi minus x. Okay? Now that, remember, if we want to write this function as a sum of sine waves, we have to write this as a Fourier sine series. And we've done this before. This is not the first time we've seen this. So hopefully you remember the Fourier sine series of this thing. So it's n equals 1 up to infinity. If you don't, that's perfectly fine. You can just look it up in your notes. 4, let me give myself a little more room for that. 4. So that's 4 times 1 minus negative 1 to the n over pi n cubed times sine of nx. So now it's tempting to say, oh, bn is this, but that's not quite true. Bn sinh of n pi equals that. So we have to equate, these two things. Okay? So what does that mean? So that means that, how do I want to fit this in? Let's write this down here. So we have bn, I don't think you're going to be able to read that. So we have bn sinh of n pi equals 4 times 1 minus negative 1 the n over pi n cubed. In other words, Bn equals, let's do the bottom first, because I don't know how wide that's going to be, pi n cubed sinh of n pi, and the top of that is going to be 4 1 minus negative 1 to the n. So this is our Bn. So in other words, our particular solution is this thing right here, where Bn is equal to this creature. So that tells us that, let's write that out, u of, I think I can fit this in here, u of xy equals n equals 1 to infinity of pi n cubed sinh of n pi, remember this whole thing is just a number, times 4 1 minus negative 1 to the n times sine, oh, I can put that in a little better, times sine of nx times sinh of ny. So this, let me box that extra, this is our particular solution. This is the surface. If you were to graph this in your favorite graphing calculator or program, it would be this surface right here. And now notice, again, this is just a number. In the x direction, we have a sine function. So in the x direction, this thing is, you can think of it as like a sine function. These things are all sine waves, and if we were to extend them for all x, in a sine series, look like that, down, up, down. Whereas in the y direction, we have a sinh function. So we could extend this thing to the whole xy plane by making this into a sine series in the x direction, making this, again, this, down, up, down. And then in the y direction, it would be a sinh function. Remember, a sinh function is, or what that looks like, that's like this. So in the y direction, it would not be periodic. It would just be going off forever and going down forever in that way. So anyways, I don't know if you took anything from that, but this function, if you were to graph it, is precisely this surface right here. And it is the steady state solution to the heat equation given these four boundary conditions regardless of initial conditions. Okay, so now we have two more of these things. Trust me, it's not that bad. We did most of the work on the previous one. So here is Laplace's equation again, and here are 3 zero boundary conditions, and here's a fourth boundary condition. So let's sketch what this looks like. So as before, we have, so this is the x direction, and this is the y direction. This is the point 0, 0. But now, this side is given by a parabola, and the back edge is going to be 0. So we have almost the same thing as we did on the last equation. It's rotated 90 degrees. That's the only difference. So now the surface for this, I can probably actually draw this a little bit better, just like this. So the surface is going to look like something like this. Maybe it goes like that. Okay. So this PDE is this function u, a solution, represents the graph of this function, which is the steady state solution to the heat equation given these four boundary conditions. Okay, so we could go through the whole process that we did last time to solve it, but we don't need to. This is the same thing. It's just we've switched the position of x and y. So we know the solution. We could just write down the same solution that we had in the last problem, but for every instance of x, put a y, and vice versa. So this is the same. Let's write this down. This is the same as example 1a, but but the roles of x and y are reversed. So by symmetry, we know that the general solution of x, u of x, y, so it's the same thing as, let's just write the same thing down, just switch the values of x and y. N equals 1 to infinity, let's do the bottom first, pi n cubed, sinh of n, oops, that's not a sinh, that's a, so I need sinh of n pi, and then the top is at 4 times 1 minus negative 1 to the n, and then we have sinh of nx times sine of n of, not, sine of ny. That makes sense? So this is the solution to this boundary value problem, and that's it. Okay, so here's the last example. So we have this boundary value problem. This is Laplace's equation. We have 0 boundary conditions here, and then we have these 2 non-zero boundary conditions in the back. So let's sketch this before. So this is the x direction. This is the y direction. This is the point 0, 0. And then in the back we have this, we have this. So I don't know how I'm going to draw this, but I will try. I guess that's okay. So notice this is literally a superposition of the first 2 examples. So let's write this down. That this is a superposition of examples 1a and 1b. And literally, if I add up the boundary conditions, for example, 1a, we get 3, this was 0, this was 0, this was 0, and this was non-zero. If we take that and we add up the boundary conditions from 1b, 0, 0, 0, non-zero, we get the boundary conditions here. So it should not be surprising to know that that this graph is literally a superposition of the 2 solutions to 1a and 1b. So the solution is just the sum of these 2 solutions. So let's actually sketch. How do I want to do this? So let's draw this first. So here's sort of a cartoon of this. So example 1a, we have this surface. Example 1b, we have this surface. That's not a very great drawing. And if we add those together, we get this surface right here. Doesn't that make sense? Example, this is 1a, this is 1b, and this is 1c. So let's add our functions together. So u of x, y. So there's that, so both of them have this sum from n equals 1 to infinity. They both have this pi n cubed sinh of n pi on the bottom, and they both have this 4 times 1 minus negative 1 to the n on top. And then what else is in there? So the first one is sine of nx sinh of ny, and the second one is sinh of nx times, or times sine of ny. So this, without doing really any math, this is the solution to this boundary value problem up here. And this is in general, I'm not going to give you any for homework, but this is in general how you would solve a complex boundary value problem, say on a square region, when all 4 boundary conditions were non-zero. Now, if you really had to, you could just one by one do what we did in examples 1a and 1b, make 3 of them 0 and 1 of them non-zero, solve that, do that 4 times, add them together, and you would get the solution to the boundary value problem where 4 things were non-zero. So that would be an absolute nightmare, but try to picture what it would be like if we had a square region and the temperature, I don't know, maybe the temperature up, maybe it wouldn't be that bad. Maybe the temperature here would be 1, maybe the temperature would go down to 0 here, maybe the temperature would be negative, something like a parabola here, and maybe it would go back up like this. So, you could come up with a PDE where the boundary, where the temperature at the boundary was something like this, and you could solve it using this approach.